Hey everyone, and welcome. All right, today we are diving deep into the fundamental rhythms of the universe. From the tiniest little wiggle to the most massive, powerful wave, it all starts with the simple and kind of beautiful physics of oscillation. I know, it sounds like a weird question, right? But a vibrating guitar string and a massive earthquake are actually governed by the exact same physical principles. And stick with me, because by the end of this, you're going to see exactly how they're connected.
Okay, first things first, let's get a couple of terms locked down. You have periodic motion. That's literally anything that repeats itself over and over. Think about the Earth orbiting the sun. That's periodic. But oscillatory motion is a special kind. It's a repeating to and fro movement around a central point, kind of like a pendulum swinging on a clock. So here's the takeaway. All oscillations are periodic, but not all periodic motion is an oscillation.
All right, so now we're going to zoom in on the purest, most perfect kind of oscillation. This is the blueprint, the ideal version. It's called simple harmonic motion, or SHM for short, and it's really the foundation for pretty much everything else we're going to talk about.
So what's the secret sauce that makes SHM so simple and harmonic? It all comes down to something called the restoring force. This is the magic ingredient. It's a force that is always trying to pull or push the object back to its starting point, its center. And the farther you pull the object away, the stronger that restoring force pulls it back. That predictable relationship is the key.
Okay, let's actually watch this happen with a classic block and spring. When it's just sitting there, it's at equilibrium. Everything's calm. But then you pull the block to the right. Instantly, the spring creates a restoring force trying to yank it back to the left. When you let go, it shoots past the middle, and now it compresses the spring. So what happens? The restoring force flips directions, pushing it back to the right. And that cycle, that constant back and forth, is the oscillation, driven completely by that restoring force. So in this little dance back and forth, there are two really important spots we need to name. That center point, where it started, we call that the mean position. That's where our block is moving at top speed. Then you have the farthest points it reaches on either side. We call that the amplitude. That's where it runs out of steam, stops for just a split second, and turns back around. Okay, let's talk about energy, because this is where it gets really cool. When that block is stretched all the way out to its extreme position, the amplitude, it stops for an instant. Right at that moment, all of the system's energy is stored up in that stretched spring. It's 100% potential energy, like a drawn bowstring, just packed and ready to fly. And then whoosh, as that block zips right through the middle, the mean position, where it's moving the fastest, all of that stored potential energy has been swapped out for pure motion energy. It's now 100% kinetic energy. So what you see is that in a perfect world, right, with no friction, the total amount of energy never actually changes. It just gets passed back and forth, constantly trading between potential and kinetic. It's this beautiful, constant exchange that keeps the whole oscillation going. Okay, so we've got a handle on a single wiggle. That's cool, but what happens when you start connecting these wiggles together? This, my friends, is where things get really interesting. Just imagine a whole line of those blocks and springs we saw all hooked up to each other. If you poke the first one, does that wiggle just stay put? Of course not, because it's connected to the next one, and that one's connected to the next one. It passes the disturbance along. That disturbance, it travels right down the line. And that traveling disturbance, that's a wave. And here is the absolute key idea. You gotta get this. A wave moves energy from one place to another, but it doesn't actually move the stuff it's traveling through. The little bits of the medium, they just wiggle in place and pass the energy along to their neighbor. Now, it turns out there are two main ways these wiggles can wiggle. In a transverse wave, picture making a wave on a rope. You move your hand up and down, but the wave itself travels forward, away from you. The motion of the rope is perpendicular to the motion of the wave. But in a longitudinal wave, the particles push forward and back in the same direction the wave is traveling. Sound is the perfect example here. It's basically a series of compressions squishing through the air to your ear. All right, this is a fun one. What happens when two waves meet? When they try to be in the same place at the same time? Do they smash into each other? Do they bounce off? Nope. The answer is actually way cooler and way more elegant. It's called superposition. The principle of superposition sounds fancy, but it's incredibly simple. It just means that when waves overlap, you just add them up. If two wave crests meet, they add together to make an even bigger crest. If a crest meets a trough of the same size, they add up to 0 and cancel each other out. Simple as that. Okay, let's watch this play out. We've got two little pulses on a string, and they're on a collision course. One's a hill and one's a valley. Now watch what happens when they meet. Okay, here they come. They're overlapping, and for just one incredible mind-bending moment, the up and the down perfectly cancel each other out. For an instant, the string is completely flat. It's wild. That's what we call destructive interference. But here's the really amazing part. The very next moment, they pop out the other side completely unchanged and just keep on going as if nothing ever happened. They pass right through each other like ghosts. And you know what? This same idea is how we get standing waves. On a guitar string, a wave travels to the end, reflects back, and interferes with itself. That interference creates this stable, vibrating pattern with spots that don't move at all. We call those nodes. And that is exactly how a guitar string makes music. It's superposition in action. Okay, so we've gone from one little wiggle on a spring all the way to waves passing through each other. Let's zoom back out now and see how these simple ideas explain, well, a huge part of the world around us. So remember that question from the very beginning, a guitar string and an earthquake? Well, now you know. The guitar string is all about creating those standing waves. An earthquake is just unleashing massive seismic waves through the Earth's crust. But it goes so much further. The sound you're hearing right now, the light you're using to see this, radio signals, all of it, it's all built on the fundamental physics of wiggles and waves. There's this quote from one of the sources that just nails it. Seriously, if you can really get your head around this core idea of oscillatory motion, you've just been handed a key that unlocks a massive chunk of how the physical universe actually works. So I'm going to leave you with a big, kind of trippy thought to chew on. If the atoms that make us up are vibrating, and even entire galaxies have these huge oscillatory patterns, could it be that we're all just part of one giant cosmic vibration? Something to think about. Thanks so much for joining me.